Okay, welcome to Lesson 2. The topic of discussion for today is going to be power. Power is defined as the rate that work is done or the rate that energy is converted. For our purposes, we are going to be using the definition of the rate that work is done. Seeing as how power is defined as the rate that work is done, we are going to express it as being equal to work over time. When calculating something like power, we already have tools at our disposal from the previous lesson to figure it out. First, we have voltage. Now, voltage we talked about was um, how bad current wanted to flow in the system, the electrical pressure of the system. The way that voltage is expressed is in terms of work per unit charge. For every charge that we're dealing with, it's how much work is being applied to it to make it want to flow through the system. We also have current, which we defined as charge flowing through the system. The current is the amount of charge flowing by a point at any one time. So if you were to look at a point on a wire and measure how much charge is flowing over it per second, let's say, so maybe it's coulombs per second, for instance, for when we're talking about amps, that's how we define an amp. You would think it's charge over time. Now, if you notice, all the terms we need to find power are already available. If you look at this equation here, we see what we define as power, work over time. We see here what we define as voltage, work per charge, and we see what we define as current right here, charge per time. If you multiply this out, you'll find that the units of charge are going to cancel. So these are going to cancel out. It's not a very good color. Charge down here and the charge up here will cancel, and what you're left with is work over time. This means that power is equal to current, which we express with the letter I, times voltage, which we express with the letter E. So power is equal to current times voltage. So if you have a system with some voltage across a component, and then you measure the current going through the component, you multiply those together, you will find the power that the component is consuming. Now, power can take many forms. It can take the form of doing work over time in the sense of like a motor, the way that a motor would spin a fan or propel a pump to move fluid through a system. It can also be in terms of heat. So if you have a heater, the amount of heat being produced over time, the energy per time or work over time would be expressed in terms of power. We are going to talk about power in watts. This is the unit of power. And as you would imagine, since power is defined as work per time, a watt is a joule per second. Now, if you look, we have current and voltage equals power. But we've already established in our previous lesson that current and voltage have an established relationship within a system. They relate through R. Current is equal to voltage divided by resistance. That means that from this equation, we can actually make two more. This will come in handy whenever we have to calculate the power in a system where maybe we don't know the voltage and the current. We have two other equations where we utilize R. The first one is power is equal to the voltage across something squared divided by its resistance. Now I got that by taking Ohm's law and replacing current with voltage over resistance, okay? Because current is equal to voltage divided by resistance. So I plug that in here, and what I get is voltage squared divided by resistance. Using a similar method, we can create the third equation, power is equal to current squared times resistance. In this one, I subbed out for E. So instead of E, I put current times resistance because I can just move this R over to this side of the equation and then plug in current times resistance for E, and I get this equation. So these equations here, one moment, let me clean up the board a little bit. these equations right here are our power equations, these three. So to review, power is the rate that work is done or the rate that energy is converted. We care about the rate that work is done. So that means that power is work over time. Since voltage is the work being done per unit charge, and current is the amount of charge flowing per time, if I multiply them together, the charges cancel and I'm just left with work over time. So I'm able to identify that power is current times voltage, okay? And then I can transform this equation using our previously established Ohm's law into these two as well. So these three, you're going to use a whole bunch, okay? And when you calculate power, it comes out in watts. So watts is joules per second. And based on this equation, if you multiply current, or in this case, the unit would be amps, times volts, you're going to get the watts that are dissipated in whatever you're looking at. It's good to have all three of these memorized because in some instances you may know, let's say it's a resistor and you had a clamp-on ammeter and you measured that there was 2 amps moving through it and the resistor was 2 ohms, you would therefore be able to find out that the amount of power dissipated in the system is 8 watts because 2 squared is 4 times 2 ohms is 8 watts. You could use this equation, but then you'd have to figure out what the voltage across the resistor was. So if you know all three of these equations, you can cut steps out of a lot of problems that you're going to encounter throughout your career. All right, so that's everything for lesson 2 on power. I'll see you in lesson 3.